Hello friends, so today we talk about the process capability for normal data. In this video, we'll talk about the basic concepts and assumptions of process capability for normal data. So let's get started. So what is process capability? Process capability is the ability to produce products or provide services that meet specifications defined by the customer's needs. For example, a manufacturer of photocopiers requires that the width of a rubber roller must be between 32.523 and 32.527 cm to avoid paper jams. Capability analysis reveals how well the manufacturing process meets these specifications and provides insight into how to improve process and sustain your improvement. Before assessing process capability, you must ensure your process is stable. An unstable process is unpredictable. If your process is stable, you can predict future performance and improve its capability. The capability of a process should be consistently measured and analyzed. Capability analysis can help you answer the following questions. Is the process meeting customer specifications? How will the process perform in the future? Are improvements needed in the process? Have you sustained these improvements, or has the process regressed to its previous and improved state? We analyze process capability with capability indices such as CP, PP, CPK, PPK, and sigma level. Recall ABC company from chapter 4. They manufacture parts to have a 10-inch uh, diameter. Due to variation in the process, each part's diameter isn't 10 inches exactly, but as long as the diameter of a part is between 9.95 to 10.05 inches, it will fit the customer's requirements. Specification limits are the minimum and maximum values that are acceptable for input and output variable of a process. The part diameter requirements at ABC company are examples of specification. In this chapter, we will examine the performance of a process relative to specification limits. A process can have a lower specification, an upper specification, or both. To ensure that the parts meet specification, the process must consistently produce parts according to these specification limits. If the part quality is poor, customer satisfaction may dwindle and ABC could lose sales. To assess process stability, we use control charts. The H-bar chart indicates that the variation in part dimension and part diameters is consistent over time. Not necessarily, this H-bar chart is stable over time, but what it looks like this. According to the control charts, the process is stable, but look at the histogram of the past diameters used to create this chart. Notice that the mean is much higher, much greater than 10, and the process consistently produces parts with 10-inch diameters, which is of the target of 10 inches. So this process is stable, but all diameters are of the 10-inch target. So that's a difference between control limits and specification limits. Control limits are determined by the process, and specification limits are determined by the people. Then how do we determine if the process is meeting specifications? To assess the performance of a process relative to a specification, we can calculate capability indices. A capability index incorporates the process and spread and the specification spread. In other words, the spread of process data is compared to the width of the specification interval. If a process is able to meet specification, the process spread is smaller than and within the specification spread. The specification spread is sometimes called tolerance. If a process is not capable of meeting specification, we have to evaluate why. Is there too much variation? Is the process off target? Look at these three histograms of process output. Why are these process data not meeting specification? All of these processes are producing parts out of spec. When our process isn't capable, the quality of our products and services suffers. To improve our processes, we study process capability. So how do we quantify capability? In this chapter, we will learn several ways to measure process capability using descriptive indices. The index we use depends on our organization, audience, and the type of data we are evaluating. For example, a simple way to assess capability of a process is to calculate the percentage of parts or services outside of the specification limits. Look at this example of 100 parts diameter. There are 18 parts out of 100 parts have their diameters smaller than and larger than the upper and lower specification limits. So 18% of the part diameters are out of the specification. We can also look at the parts per million outside of specification, commonly called ppm. This number is another way to interpret the percentage outside of the specification. ppm reports the observed value relative to 1 million parts. The percentage of parts outside of the specification limits and parts per million are simple methods of assessing capability. But what if the process data look like this? The capability estimates are 0, percentage out of spec 0, and ppm is 0. So if we use these values alone to estimate capability, we wouldn't know that our process needs to be improved. In the next few sections, we'll discuss other capability indices that account for the location of the process data relative to the specification limits. Let's review. Capable process consistently produce products or services that conform to the specification. Specification limits are determined by people, and control limits are determined by the process itself. Capability indices help us determine if a process is able to meet specifications. Percentage out of spec and parts per million out of spec are two simple ways to assess capability. Before calculating capability indices, we must check two crucial assumptions about the process. The process is stable over time, and the normal distribution is an adequate fit to the process data. So let's go back to ABC company. Suppose the production manager signs a contract to sell parts to a big customer for the next 24 months. A quality engineer tells the manager that the part diameters of the manufactured parts meet specification. If that's true, so then what can we assume about the part manufacturing process at ABC over the next 24 months? Okay, so the answer is D. The path diameters will be consistent over time. If the quality engineer says the process is capable of meeting specifications, then we assume that ABC is able to provide quality paths over the life of the contract. In other words, the process is stable over time. If the process is not stable, then our capability indices are only applicable to the sample we have collected and not to the process over time. In general, we first check the process is in control. Remember what in control means? If we draw a sample from process on Monday at 8 a.m., that sample will be similar to one drawn on Tuesday at 2 p.m. As a result, we can be confident that the process does not significantly change over time. We use control charts to check this assumption. Not only do we assume that the process is stable, we also assume that a normal distribution is an adequate fit to the data. Remember, a capability study tells us how well a process can produce outputs within the specification limits. To do this, we need to know the distribution of individual values produced by the process. The most common way to do this is to assume the data follow a normal distribution and then use it to estimate the capability of the process. Although the normal distribution is commonly used to describe process data, it is not always the best fit for many processes. In a later lesson, we'll learn how to prepare non-normal data for capability studies. Let's review. Remember the two key assumptions for capability studies. The process must be stable over time and the data uh, follow a normal distribution. We learned how to study process stability in the control charts chapter. In the next lesson, we'll learn how to check that our data are adequately modeled by a normal distribution. Thank you for your listening. In the next lesson, we'll talk about testing for normality.